The concept of place value in numbers is absolutely crucial and fundamental to our understanding of the number system that we use, and it's something which is taught quite low down in primary schools, and it's something that we don't really think about. It's obvious, it's always been there. Isn't that the only way that we can have numbers? Well, it isn't. Just a quick reminder of what I actually mean. If I take a number, let's have any old number, let's have 2, 3, 7, 6. Okay. Each of those digits in that numeral has a value depending on where it is in the numeral. The digit to the right-hand end is 6 ones, 6 units. So that is 6 times 1. This one is tens. So that is 7 tens. This one, the next one along, we're now up to hundreds. So that's 376. So that is hundreds. The next one is thousands. I'm sure we all know that. It's relatively obvious. Every time we add a digit on the left-hand side of the number, that digit is worth 10 times as much as the next one along, and so on, and so on, and so on, as far as you'd like to go. As I say, that's the way we write numbers. It seems obvious, but that's not the only way to write numbers, and to see how important that is, it's worth just having a look at number systems which don't use that convention. Now, historically, there have been many, many different ways of representing and writing down numbers over the millennia. They do have certain things in common. Almost universally, they are based on the number 10. That's not because the number 10 has some kind of magical properties mathematically that makes it particularly suitable. In fact, computers, which have to be very, very logical in the way that they work things out, use a number system based on the number 2 for all their internal calculations, because that's what works best, certainly for a computer. The reason that humans use the number 10 is purely biological. We tend to count naturally on our fingers, and we have 10 of them. So it's natural that we should use base 10. Effectively, you can count up to 10 fingers yourself, one person, so that is essentially this number. But then you need to keep track of how many times you've done that. Maybe have a different person who sticks a finger up to count how many times you've counted 10, which is effectively that one, and then again for that one, and again for that one. Makes perfect sense. But that's not necessarily the most easy and obvious way of counting. For instance, the ancient Egyptians didn't actually do that. And Roman numerals are similar. If you want to know about Roman numerals, a video down here somewhere, link in the description, as all the YouTubers say, and there's stuff on the website. But getting back to this, ancient Egyptian numbers were based on, well, it's certainly on the base 10. For the 1, they had a 1, which is believed probably to be representing one finger. For 10, they had a little arc shape like that, which is apparently a piece of rope. And for 100, they had a coil of rope like that. Okay, fair enough. But there weren't any other numbers in between. If you wanted to make up a number, then you had to have several of those, several of those, several of those. I haven't mentioned thousands, so if we just look at 376, part of that number, and we see how the ancient Egyptians would have written 376, they would have had 3 of those. Okay. 7 of these. And 6 of those. And that's how they would have represented 376. If you think about it, that's reasonably logical. You can work out what the number is from that, but you do have to do some counting. You can't immediately see. You'd have to count those, and you have to carefully count those to make sure you've got it right. And it's very difficult to do certain kinds of arithmetic with this number. If I add a bit more to my 376 to make it up to 400, then what I would then do is I would have 4 of these things, but nothing else. All the rest of the number would have disappeared. So the number has actually become a larger number, but most of the digits have disappeared, and we've got that. Roman numerals, as I mentioned earlier, are much the same. Roman numerals, you would have 300 and 50, 60, 70, 5, 6. They've refined the system slightly. They also have letters for 50 and 5, and they have a letter for 500 as well, to avoid having quite so many things as the ancient Egyptians had. But still, if you make it up to 400, you would have just C, 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 or they didn't even do that, because 500 was the letter D, they would have C, D to represent 400. Now all this is a bit confusing and illogical when compared to the system that we have. And this is because we have this concept of place value. If you look at the last digit in any of these numbers, it doesn't really tell you a lot. The last digit in one of these is always units. It's always 6 or whatever ones. But here, this digit actually represents 500, and that digit represents 100, and that's some subtractive shortcut that the Romans used to avoid having to write out that. This is not as sensible, is it? It makes arithmetic with these numbers much more difficult. It's nothing like as logical and straightforward as this system. So things have not always been quite as obvious and quite as easy as that. This is called the Hindu-Arabic numbering system because it was originally developed by Indian mathematicians in the 1st to the 4th century AD, taken up by Persian and Arabic mathematicians a bit later, 8th, 9th centuries, and then eventually it came over into Europe and took over from whatever other systems we had in Europe. And now most of the world use this system because it's logical and because the place value is actually very powerful. There are things you can do with these numbers that you can't very easily do with those ones. Adding and subtracting isn't too bad with these. Multiplying is a bit of a nightmare. That kind of stuff, multiplying, dividing, becomes very difficult. Egyptians found a way to do it. They have lots and lots of calculations to do to make pyramids and things. They worked out a way of multiplying, which you might like to look into. It's quite interesting. I'm not going to cover it. Doing it with these is much easier. If we want to multiply this number by 10, you probably say, oh, stick a 0 on the end. Yes, but what we're effectively doing is shifting it one place to the left. The next digit, of course, is 10,000. So to multiply that by 10, we shift the whole thing 2376, one digit along to the left. So if I rub it out in here and put it one digit further along, and then put a 0 on the end, I've multiplied it by 10. I haven't had to change any of the digits. If I multiplied these by 10, I'd have to change all the digits. It would be a mess. It would be very difficult. Similarly, to divide by 10, you move one place to the right. Pink bits. I've drawn some pink lines. That's because that represents to me the decimal part of the number. Because we have to line up these numbers when we're using them. If I was adding up numbers here, it's very important that I get them lined up, and that's one of the crucial things about the place value of numbers. If I was adding to that number, the number 342, it matters where I put it in this sort of grid of columns. Because the 2 has to be the units. So I can't put 342 starting at that end of the number and then add things up. That wouldn't make sense. This is 300, not 3 lots of 10,000. So that would be incorrect. So I would have to do it at the other end. So if I remove the 342 and put the 342 there, that makes sense. We line up the right-hand end of the number. Well, actually we're lining up the decimal point. If you have a decimal number, then it's not the right-hand end of the number that you line up, it's the decimal point. So if I put decimal points here, And imagine this number has a decimal part at the end. This could be 0.5, perhaps. This one could be 0.625. So everything is lined up where the decimal point comes, which is at the end of the whole part of the number. So if there's a decimal part, one of them might extend further to the right. As long as the decimal points are in line, it makes sense. And if you think about it, that's because you've got to get the numbers in the right columns. And these columns here, this is 0.1, this one is 0.01, and this one is 0.001. Again, they get a tenth smaller, 10 times smaller as you go to the right, 10 times bigger as you go to the left. None of that is possible with this kind of number. And as you get into more complicated sorts of maths, you'll find that there's an awful lot that you can do that depends on lining up the digits correctly, and you've got to make sure that you do. Whenever you're doing things with numbers, make sure that you line them up correctly, and remember, it's the decimal point that has to be in line. Okay, I hear you say, enough intellectual waffle about Hindus, Arabs, ancient Egyptians, Romans. How can we actually use this information to help us to answer questions when we're given a massive number such as that, and ask things about the values and the relative values of the different digits in the different positions? Well, I'm doing a video on exactly that, which you now need to click through and watch.